Okay, so let's chit chat about this spiritual energy. And I want to play out two different scenarios. And I want to start with one that makes sense and the other one that doesn't make sense. But they work mathematically. So, situation number one.
Alright, you know what? You guys get away from me. Alright? If you're gonna take my info, stop. No, I'm freaking wrong. Alright? Get away from me. Get away from me. This calculation were wrong.
Shut up!
It's barely Monday, bro.
It's Monday.
It's Monday, bro. Please. Dude.
So, here's the story. Do you all agree that for energy to be conserved, at any point, potential energy plus kinetic energy has to add up to a constant?
Yes.
Cool with that idea. Okay, one of the great conservation. So to make this simple, just to make the pure mathematical model work out, I'm just going to let the constant be 20 joules. Okay, it could be any number. I'm just going to make it simple, and I'm just going to let it be 20. Okay? Now, so here's what you want to look at. Initially, here's what's going to happen. Is that I'm going to take two positively charged particles. Okay, because it's going to make the math simple. And I'm going to have one positively charged particle way out here, and I'm going to shoot it towards the other positively charged particle. Okay? Start with this. So, to make this simple, okay, I'm going to say that initially, the potential energy has a value of 6, and the kinetic energy has a value of 14. Okay? I don't care what the number are, I just want to look at the mathematical model. Okay? So 6 plus 14 is going to equal 20. Now, this is what's going to be important in terms of this OOI. This OOI is K Q1 Q2 over R. Right? Okay? Calculation of OOI.
Is this a problem?
No, I'm just trying to paint the big picture. Okay? This is not one of the specific problems, this is the big picture. Okay? It's just a constant.
Oh, okay.
Whatever the constant is for the system. Okay? Now, so as this goes through, because of the fact that the Q's are both positive and K is some number, the top part of this number isn't going to change. Okay? It's just going to remain as some number, KQ over R, right? And the kinetic energy is going to be 1/2 mv squared. Again, I don't care what the mass is. This is just going to be a pure mathematical model. Okay? So here's what I want you to look at. Is that as these two approach, okay? As these two approach, what's going to happen to the amount of kinetic energy?
Down. Wait.
Why?
Oh.
Because U goes up.
Okay?
U goes up. K goes up.
So this is like throwing a ball up a hill. Okay? Like throwing the ball up a hill. So as it goes up, what's going to happen to the kinetic energy? It's going to go down. Well, what's going to happen to the amount of potential energy?
It goes up.
It's going to go up. Now, this R here, that's the distance between the charges. Okay? So as this approach, the distance between those 2 points is going to do what? Increase or decrease? As these positive charges approach, R is going to become smaller. So you're going to be, are you going to change the numbers up on top?
Impossible.
That's as long as this K is the same, which hopefully it is, otherwise the universe has changed. And the charges remain the same. The top is just a number. Again, this is just a mathematical model, just to show you how this thing works. Okay? So, as this thing is approaching, the top number is going to stay the same. You're going to be divided by the distance that separates them. Okay? Not the distance above, like the Earth. This is the distance that separates these points. So, let's say, for example, this is at a distance of 2 meters. Okay? So, let me make sure I got that right. No. I screwed that up. No. That would be 6. I transposed the 6 and the 2. Yep.
Big word.
You know I can't do it.
What?
Yeah, I know. Ryan, you know I can't do
Wow.
it. Contribution. Wow. Ryan, you know I can't do it.
Let me go ahead and write down some more
Ryan, you
numbers.
can't. Ryan, you can't.
Oh,
trans-
oh,
Ryan, you
Oh,
can't do
oh,
it.
there
either.
it
is.
Ryan, you can't
Oh,
transpose. Ryan, you can't transpose. I'm not doing
Children.
neither of us. I get it better than you did. Oh, sure. Oh, sure. That's why you're first.
To erase that and rewrite it. Thanks, Sparkle.
Okay, so here's what I want you to see. Is that this is starting off as these positive charges that are like 6 meters away. Okay? So at 6 meters away, you're going to have a certain amount of kinetic energy and a certain amount of potential energy. So as it approaches, that's like rolling this thing up the hill. So my kinetic energy is going to get smaller, but my potential energy is going to get bigger. Okay? So that everything still adds up to 20. Okay? Law of conservation. Oh, that's it. That's kind of related to that. So here's the story. If you were to draw a graph of OOI, and you would have radius. So here's 2 meters, here's 4 meters, here's 6 meters. What would the graph of the potential energy look like?
Top left, top.
So at 2 meters, that's when you're going to have your highest value, and this line is going to come down like this. Okay? What would the kinetic energy line look like?
Exactly the opposite. Inverse.
Right? That would go something like this.
Okay, so
What?
I get the direction where it starts, but like, what's with the curvature versus?
Because they can never get to
Is it
zero.
just a square?
Yeah,
It goes
it's
down.
like an asteroid.
And
Okay?
kinetic goes up.
Now, this one is not the problem. This is not the problem. No one has a problem with this. Okay. Talk to the law of conservation of energy. The problem comes in when you begin to look at when you have opposite charge. Now, let's talk about changes in voltage, okay? Because this is some of the questions on the assignment. Let's say this is what's creating the field. So, if this is what's creating the field, and let's say that you only have one positive charge. If you only have one positive charge, and that's what's creating the field, when you plot those lines of voltage around there, okay? What do you notice about the voltage lines?
It decreases.
As they go away, the voltage becomes smaller. Okay. Now, this is where this takes a little bit of a leap of faith. So, imagine, if you will,
What's going on?
So here's positive charge. So this is the one that's creating the field. Okay? This is what's creating the field. So imagine that you have a line here. If you go back to this, we had like 9 and 4, then like 3. So around here, this would be like a 10-volt line. This would be like a 5-volt line. This would be like a 3-volt line. Okay, something like that. So as you go down, the positive voltage gets smaller, right? So if you were to push a positive charge closer to that, are you going to undergo a change in voltage? Yes. Now, what's on your handy-dandy equation sheets, let me see this, is that you have delta UI equaling Q delta V. Okay? Now, here's what I want you to look at. This is where these fit together. If you have a positive charge, okay, that's what's out. That's not what created it. This is the size of the boulder you are pushing. Okay? This is what you are pushing, which I'm going to make that be a positive value. Now, here's the story. I want to push it from 3 volts to 10 volts. Okay? Does it want to go in that direction? No, it does not want to go in that direction. So I've got to push it because it's repulsion. Repulsion. Boom. So if you look at this charge, that's going to be whatever that positive charge is. Now, delta V is always final minus initial. So I'd have 10 minus 3, I'd get positive 7 volts. Now, what are the units for voltage? Joules per coulomb. Joules per coulomb. So if I take joules per coulomb and multiply that by coulombs, I get which is what energy is measured in.
So
Okay?
delta U is work.
Huh?
Delta U is work.
Yes. Because work is any change in energy. Okay? Now, so if I push it up the hill, I would have a positive change in UI. Okay? Which would mean I would do positive work because I've got to push it from a low positive voltage to a high positive voltage. So, notice that this only happens if there is a change in voltage. Okay? Which is equivalent to the idea that work equaling force times distance, right? If I just hold up this baseball, am I doing work? No. There has to be a change in the displacement of the direction of the force. So if I just hold that positive charge in place, am I doing any work? No. Because there's no change in voltage. Okay? So without a change in voltage, there's no work. So obviously, the bigger the change in voltage that there is, the more work that you're going to do. The bigger the charge is, the more work that you're going to do. Okay? That makes sense. Okay. Everybody cool with this?
Yeah.
Now, what if I take that same positive charge, but I in effect like lower it back down? I go from 10 volts to 3 volts. What's going to be the sign of my delta V? Negative. So can my delta V be a negative value? Absolutely. Absolutely. Voltage can be a negative value. But visualize this. Does the positive charge basically want to roll down the hill?
No.
Yeah.
No.
Roll down the hill.
Does the positive charge want to roll down the hill?
Towards the positive?
Yes, why?
Because
That's
that's
like
hell.
charges.
Because it's repulsion, right? It's trying to slow down, it's trying to go down the
Hold
hill.
up. What?
So,
There's a positive on the top of the mountain. You're trying to push it
There's
closer.
a positive on the bottom?
No. Positive and positive.
No, there's nothing at the bottom.
Oh,
No.
okay.
We're only talking about positive charge.
That was so
Oh, okay.
We're only
Yeah,
talking
we're
about
going down. We're going down.
You know
sitting
what?
at the top of the hill
No, we're yelling.
that you climb to define the median height. Okay?
No, you can say temper, that's okay too.
I don't know what you're.
It's gonna be like
Maybe I don't know.
So,
Only in left hand, bro.
the positive charge wants to go down the hill.
Yes.
Cool with that? Positive charge wants to go down the hill. So you have to prevent it from going in that direction. So you're pushing up, but it's going
Down.
so the force that you're applying is in the opposite direction that it wants to go. Therefore, you're going to do negative work. Guess what? Your delta U is going to be a negative value. Okay?
Interesting.
So it works out conceptually and it works out mathematically.
That makes more
Okay?
sense.
Everybody got that one?
See.
I throw it up, it slows down, I build ooey, I lose kinetic. We're good. We're good on that.
Oh, if you're pushing it away, it's negative.
Just chill out.
No, number 5 is
We'll
fine.
get to that.
Let's
Dude,
go
how
slow.
physical?
Number five.
Hey, let's give
Now,
Question 5?
that one isn't the problem.
I was like, whoa.
That one is not the problem.
positive, negative.
Positive and negative is the problem.
Uh-oh.
Okay.
I remember
So,
the question like that.
problem
Hold on.
Just
This
my
is
fault,
like
my
this is like
fault.
Friday work, bro.
You guys log in, please.
Oh my
Yeah,
god.
This is if I do my
okay? I'm positive and negative value.
No, I don't remember like.
And I throw the negative at the positive.
Yeah.
Okay? Would still U plus K still add up to a constant?
Always.
Yeah.
They always.
Everybody
hell
cool
yeah.
with that? Okay? So, just stay with me here. I'm still going to let the constant be 20 joules. Okay? Right? Now, because this is ooey, which is KQ1, Q2 over R, if they're oppositely charged, what's the sign of ooey?
Oh yeah.
Now we got a negative value. So let's say at some point, again, this is just a mathematical model. At some point, let's say the kinetic energy has a value of 26 joules. Okay? So what has to be the value of my
Negative 6.
negative 6?
Seagull 6.
So that everything adds up to
20.
20 joules. Okay? Now, let's say that that is what's associated with the distance of 2 meters. Okay?
No, I have chairs. Every single one of them except for Thomas. I'm sorry, I don't know the names of the
This is
Okay. Now, just chill out. So, when this thing is 2 meters away, it has a certain amount of kinetic energy of 26 and an ooey of negative 6. Okay? Now, here's what I want you to think through. If you start out here at 6 meters, and then you approach, and you know what's going to happen at 2 meters. So here's my question. At 6 meters away, so this is when you're at 2 meters away, this is when you're going to be at 3 meters away, this is when you're going to be at 6 meters away. When you're at 6 meters away, will the kinetic energy be bigger or smaller than what it is at 2 meters? Why?
Because it's like the planet orbiting thing where it's like, it like,
Yeah,
has
it's
to, it
not-
has to
No,
it's wrapped
that's not
up-
fair.
Hey guys, can you
It's
wrap
wrapped
it
up.
in?
It has
Wait,
to add like.
Kind of ish.
Wait, are we talking about the
We're making it unbelievably hard, bro.
Yeah, no, we're not talking.
Grab the motion.
Let's wrap it up. Let's wrap it up.
Yeah, wrap it up,
Just
bro.
wrap it
Mr.
up.
Burkamp, you should talk.
Wait, Barry, can you ask the question again?
Okay. So at 2 meters away,
Yeah.
at 2 meters away,
This is conceptual.
it has a kinetic energy of 26 joules.
Yes.
So here's my question. If you were at 6 meters away, would the kinetic energy be bigger or smaller than 26?
Let me think, Larry.
Wait.
Bigger.
Bigger. Your UE would go down.
Okay,
It's-
you have a
it's
negative
gonna go down.
value, you have a negative charge that you're throwing towards a positive.
K goes down, final answer.
K goes down.
What's it gonna do what's the velocity going to do as it approaches the positive
up.
charge?
Oh, speed up.
Speed
It's
up.
going to speed up.
Because it's a bigger negative value. And that's
No, don't. This is just kinetic energy. Do not talk about ooey. Okay,
Oh,
this is just kinetic energy. So if it has 26 joules of energy when it's 2 meters away,
I went too far.
with 6 meters, would that kinetic energy be bigger or smaller than at 2 meters? Less. Right? So let's say that that's 22 joules, and then we're going to go to 24 joules. Because as it's approaching, you're at 6 meters away. As it approaches, it's going to do what?
Speed up.
Speed up.
And
And as it speeds up, the kinetic energy has to increase because that's 1/2 mv squared.
Yes.
Right?
Yeah.
Cool with this?
Yeah.
Okay.
Hey, stop spoiling it.
Now, but everything still has to add up to 20. So, at 3 meters away, what's the value of my ooey?
Like 4.
Negative 4 joules. What's the value of my 6 meters?
Feel like -2.
So that everything adds up to 20. Okay? Now, ooey equals KQ1 KQ over R. So the top numbers are a constant. I don't know what they are. It doesn't matter what they are. It's just a constant. What's the only thing that I can change? My value of R. But the top number is going to be a negative value.
Yes, because
Okay.
the charge is negative.
So everything still has to add up to the same constant. Okay? So as it approaches, my kinetic energy is getting smaller, right? But here's the other thing. If you look at KQ1, Q2 over R, you're dividing by 6, you're dividing by 3, you're dividing by 2. Because you're dividing by a smaller radius, that's why that ooey is a negative number and it becomes smaller, but everything still adds up. Now, if you were to draw a graph of ooey versus radius, 2 meters, 3 meters, 6 meters,
Mr. Burkhead was going to do this.
what's that graph going to do?
It's going to do this. Yeah.
So,
good job, Chad.
At 2
That's
meters, you're going to be at
Big.
negative 6. At 6 meters, you're going to be at
-2.
Yup. That's what I got.
I don't know.
okay? Now, what would the kinetic energy
It's
graph
an
be?
inverse. It's split.
So if you were to draw the kinetic energy,
Bar gets split.
2 meters, 3 meters, 6 meters, at 2 meters, that's when you're going to have your,
It's like slow. Maximum. Right? The maximum.
at 2 meters, that's when you're going to have your biggest kinetic energy. At 6 meters, you're going to have your smallest. So it's going to go like this. All right?
Yeah. Wait, why is it? It's gonna go down.
Because if you look at 2 meters,
Oh, I see. I see.
Get
closer.
Faster.
Hold on, so
right?
would you be so as you get farther? How are you defining? Are you saying so as you get farther away? Are you saying you get bigger or smaller because it's negative? So are you saying it's getting closer to 0, which means it's getting bigger? So are you saying it's getting bigger? Okay.
Everybody wants to be
So I need
Okay.
to change this.
Yeah, isn't that right? My one-liner needs to be double.
now, we're going to go back to here. I'm going to swap out that positive charge, and I'm going to put in a negative charge. So before I plot any points, what's going to be the side of my voltage line?
Negative.
Negative, right? So if I plot that, boom, I plot that,
Boom, shaka,
I plot that.
Why do you want me to call my mom?
So basically, I'm going from 10 to 5. Right? So, visualize this. There's 2 unique situations. I'm going to put a positive test charge out here. Okay, so Q is going to be a positive value. I'm going to go from -3 to -10. Okay? I'm gonna go from -3 to -10.
Right.
What's just the sheer value of my delta V? So I'm going to start at -3. That's my initial.
Seven.
My final is going to be -10. So what's the value of my delta V?
-7.
-7. Everybody cool with that?
No.
Final minus initial. So whether I'm pushing a positive charge or a negative charge, would that alter the value of delta V? No. My delta V, as long as I'm going from -3 to -10, isn't going to change. My delta V is a fixed value, as long as I'm going from -3 to -10. And that's going to be -7.
Yeah.
Now, if I have a negative charge, okay? So delta U equals Q times delta V. So if I have a negative charge multiplied by a negative delta V, that's going to be a positive delta U. Everybody cool with that? We're having a positive delta U.
Wait. For the charge, the sign, we're using the.
What I'm sorry about what I'm pushing. That isn't the chart. When you delta U, it's the charge that's moving.
Shut up. What did you say?
Okay. Delta U equals Q delta V. It's the charge that's being moved across the voltage, not what's creating it.
Okay.
Okay? It's what's being pushed across the charge. Okay? And here's the reason why. Okay? Because it's just like a gravitational field. You have lines of like equal gravitational potential.
No, I'm paying attention. He's actually corrupting me. I can't.
Corrupting.
So, here's the story. If I have a negative charge, right?
Yes.
What would I have to push it or keep it from moving if I have a negative charge in the middle?
You're pushing the boulder down.
I have a negative charge, right?
Yes.
I have a negative charge.
Okay. Yeah.
I'm pushing it towards another negative charge.
Oh yeah.
I would have to push it in the direction of motion,
Yeah.
right?
Yeah.
I'd have to push it in the direction of motion.
You would have to, yes.
Okay? So since I'm pushing it in the direction of motion, work is defined as a positive value.
Yes.
Okay? Work is defined as a positive value because I would have a negative Q times a negative delta V.
I guess, bro.
Okay?
Yeah.
So here's what I want you to see. Pushing a negative charge towards another negative charge would result in a positive delta U. Just like if I had a positive charge and I were to push a positive charge toward it, I would have a positive work as well because they don't want to go in that direction either. So a charge being pushed towards another negative charge is positive work because you have to push it in the direction that it's moving.
Yeah.
Two negatives would also be positive work.
Yes.
Okay? Go with that.
Yes.
Yeah.
Now, just like if I put that positive charge out here and I've made it close and it wants to repel, if I tried to keep it from going away, I would be pushing in the opposite direction of motion and I would be doing negative work. The same thing would happen as if I had a negative charge and I was trying to keep a negative charge from flying away. Okay? So, this is what you have to understand, that equivalency between having a negative charge, a negative delta V, and a negative delta Q, which is still going to produce a positive delta U, versus two positive. The positive ones aren't the problem. It's the negative ones where it gets weird. Okay?
I guess.
Does that make sense? And there has to be, I cannot emphasize this enough, there has to be a change in voltage. Okay? Because that's like saying if I hold up a baseball, do I do work? No.
Hell no.
This is why it's delta U and not U. And that's why it's delta V and not voltage. Okay?
I see.
That makes sense. Now, y'all been talking about number 5. Let's talk about number 5.
I understand it now.
Where's my book?
Which one?
Oh, Big Mike might.
I don't have it.
You want my book?
I don't have this one.
Hey, Berg. Berg, it's in your hand.
Hey, Wyatt, what number am I on?
Berg, I think you're holding it.
Thanks for letting me know. Otherwise, I wouldn't know.
I mean, you might need your glasses. I don't know.
Where are your
That was a big
Where are your glasses, Barry?
Hey, you were rude to me a minute ago.
Oh, no. Oh,
Hey, break
so
it up.
not rude.
Yeah, you were.
Where
Whatever.
did your glasses
Okay. Which one do you want, number 5? Okay.
We want number 5.
Can you be louder?
Mr. Bird. Where are your glasses?
You might need to find them.
You want me to find them for you?
Do you want to? Do you need to find them?
Okay.
No, I think it's
Let's
the
talk
same.
about problem number 5. So, at one point in space, electrical potential of 50 nanocoulomb charge is 45 microjoule. Now, here's the other thing that you need to really begin to focus in on.
That's what he said.
And that's the difference between voltage and potential energy. So potential energy is the measure of joules. Voltage is joules per coulomb. Okay? They're related, but they are not the same thing. Okay? They're related, but they're not the same. Just like force and work are related, but they're not the same thing.
Are you talking about compact or quick? Yeah,
You guys didn't assign it, so you only did problems 1 through 4.
Oh, I'm sorry. You're right.
No worries, Mr. Bird, we got you.
Yeah, we are.
Team up.
Okay.
Teamwork makes the
So,
dream work.
problem number 5.
No, question. There is no problem.
Question.
So on question 5,
Maybe this will second.
question 5. An electron,
Let's
this
keep
is
it that way.
important. An electron moves along the trajectory. Does the electric potential energy increase, decrease, or stay the same? So, here's this positive charge nucleus, maybe lithium. And you're here, and this is going to be,
You're so smart.
and it's going to go like this. Okay?
What is that?
So, in some ways, you can look at this in terms of like a spring. Okay. So, since, first off, let's talk about this. There's a couple of ways you can visualize this. One, imagine if you were to draw voltage lines around the positive charge. Okay? Would the voltage lines be positive or negative?
Plus.
Positive. So this might be plus 20, that might be plus 10, that might be plus 5, whatever it is. Okay? So as you go, are you going to be moving across different voltage lines?
Sure.
Yes. So if this is a positive charge, what's going to be the sign of your delta V?
Oh, wait.
Wait, negative.
Negative.
What's going to be the sign of your delta V as you go from this point out?
Negative.
Negative. Your delta V is going to be a negative value. Because you're going to end up here at 5 and you're going to start at 20.
Oh, 5 minus 20.
5 minus 20. So your delta V is going to be a negative value. Right? Who?
Yup.
Okay. Delta V is going to be a negative value. Delta U equals Q times delta V.
Delta V.
So if I've got a negative delta V, and that's an electron, I'm going to have I'm going to have a positive delta U.
Because it's a negative.
Oh, yeah. I got you.
Because we just said,
Oh, positive. Yeah, I got you.
and it's an electron.
Oh yeah.
Oh,
that's-
that's
negative.
Positive. Positive. Yeah.
It smells really good.
What?
I smell like I smell these cookies.
Brother.
Bro, yeah.